So I'm going to talk about my project from the RU of summer 2022 at Indiana, and it's motivated by a problem in population biology. So the first thing is we want to come up with a model for a population, and the classical model is a diploid Wright-Fisher model. And here we're given a constant population size n, which represents the number of individuals. And so essentially, we say we know our individuals in generation G. We want to construct generation G plus 1, which is one step backwards in time. So generation G plus 1 are the parents of generation G. And what we do is for each individual in generation G, we randomly select two parents. And then for each of the parents, we randomly select one of the two chromosomes to be in the child individual. So there's two factors we considered in this project, and the first one was selfing. Selfing essentially says that both chromosomes come from the same parent. So with a probability of sigma n, as shown on the left here, both chromosomes come from the same parent, while with a probability of 1 minus sigma n, the two chromosomes come from different parents. The second factor we considered was recombination, and what we define here is the notion of a locus. A locus is just a fixed position on a chromosome. Here we denote it by a circle or a triangle. And it's possible that under a recombination event, the circle was copied from one chromosome while the triangle was copied from another chromosome. So we say with probability Rn, a recombination event occurred and the two loci were copied from different chromosomes in the parent. With probability 1 minus Rn, no recombination event occurs. So now we define the coalescence time for a pair of loci. And here in this picture here, we look at the circles. This is one loci, and the coalescence time for the circles is 2. This is because it takes 2 generations for the two loci to end up on the same chromosome. For the triangle, the coalescence time is 3 generations because it takes 3 generations for the triangles to end up on the same chromosome. So the coalescence time just tells us how many generations it took for the two loci to end up on the same chromosome. Now we have these quantities Ti and Tj, which are the number of generations until coalescence for each locus, and we're interested in the covariance of Ti and Tj. So to find this covariance, we define the state space, and essentially the state space tells us kind of whether loci belong to the same individual or whether loci are in the same chromosome. So there's 12 distinguishable states here, which were found in King et al. And for each state, we kind of obtain different results. So now say we want to find the covariance of Ti-Tj. What we can do is we can compute transition probabilities between the states and set up a system of linear equations that can then be solved for the expectation of Ti times Tj. So this is a one-step analysis of a Markov chain, and using this system of linear equations, we can solve for covariance of Ti-Tj. And while 12 by 12 is allowed to do by hand, we use MATLAB to solve this equation. And so we obtain results for 4 different scaling regimes. There's kind of 2 scaling regimes that are of interest, whether the selfing probabilities and recombination probabilities are of order 1 or of order 1 over n. So that gives us 4 possibilities. And here we have 2 plots of our results. So on the left here is scenario 1 for initial state Q12. And as we can see here, what we plot here is the analytical result, which is a straight line. And then we also simulate the Wright-Fisher model to generate these dots here. And indeed, the dots support our analytical results. And why is this result useful? So, for example, Tajima's estimator is a classical estimator for the mutation rate. And what we do is we take 2 chromosomes and then look at n loci and count the number of differences at each loci. And we can estimate the mutation rate by taking the average of the number of differences over n loci. And ideally, as n goes to infinity, the variance of this estimator would go to 0. But this is not the case, as shown in King et al. It turns out that the variance of this estimator is 4 mu squared times the covariance of Ti-Tj. So using the result we found in this project, we can now obtain the variance of our estimator. And I want to thank Professor Fan and Demetrius for helping me with this project. I really liked it, and it was a great learning experience.